Hey guys, Miss Peterson here, and welcome to our Physics in the Universe lecture on impulse and momentum. We're going to be going over what momentum is and what impulse is, as well as the impulse momentum theorem, an example problem, and what the difference is between elastic and inelastic collisions. So let's start with just what is momentum, okay? Momentum is a measure of mass in motions. And unfortunately, we ran out of m's to use for momentum because we already used m for mass in a lot of our formulas, and then m as a unit is for meters. So momentum gets a p. Now, momentum is a vector quantity, so it has a direction. It will always be in the same direction as the velocity. And the equation that we use for momentum is momentum, p, equals mass times velocity. Okay, so this P is for momentum equals the mass times the velocity. Okay, these little arrows on top are just your vector hats. Okay, so they're just showing that that momentum P is in the same direction as that velocity. And then the units that we use for these, for mass is kilograms and velocity is meters per second. So unlike energy, which we use joules, which really just means a kilogram meter squared per second squared, or force, which we use newtons, which is a kilogram meter per second squared, momentum doesn't have its own unit. It never got a special name, so we just leave it as kilogram meters per second. Okay, cool. Okay, cool. So what is the impulse momentum theorem? Now, this is one of the most convenient and used equations in physics, especially when dealing with collisions, and it just comes from Newton's second law. So, okay, Newton's second law, we know, is just force equals mass times acceleration. But if we then put in the definition of acceleration, okay, definition of acceleration as that change in velocity over time. We'll put that in for that acceleration. And then if we move the time, okay, multiply by time on this side and time on this side, we get this equation, okay? Oops. Force times time equals mass times change in velocity. And this is the impulse momentum theorem. Okay, so what this equation basically says is that the impulse is this side of the equation, the force times the time, okay, that's called the impulse, will equal the mass times the change in velocity. Now, mass times velocity is momentum, so mass times change in velocity is going to be your change in momentum. And again, from your mass times the change in velocity, which, remember, when you're doing the change, it'll always be V final minus V initial. Okay. And as you guys see, this just comes from Newton's second law. So this will always be true, and we can use it to solve all sorts of problems. Okay? But let's zoom in on that impulse part of it for a second. Okay? That impulse part of the equation is just that impact of the collision, the force times the time. So if we're looking at its units, I is impulse, equals the force, which we usually have in units of newtons, times the time, which is units of seconds. So impulse gets the units of Newton seconds. And you might be wondering, well, if impulse is Newton seconds, but we just said impulse equals change in momentum, and momentum is kilogram meters per second. Okay, let's do a quick little unit analysis on that. So impulse is a Newton second. Now, a Newton, if you remember, is a unit of force, and force units are mass times acceleration. So a Newton really means a kilogram, mass units, times meters per second squared, acceleration units. So I can rewrite Newton seconds as kilogram meter per second squared, the Newton times the second. So when it becomes that, we can see I'm going to rewrite the second squared as seconds times seconds, so we can see how that cancels out. And what's left over is just kilogram meters per second, aka the units of momentum. So a 1 Newton second is equivalent to 1 kilogram meter per second. They are equivalent units. We just use them in slightly different ways. Okay? Now, one more thing about impulse. When we are doing impulse experimentally, we're not going to have constant forces. Rather, we'll probably see something like this, where at the time of a collision, the force gradually ramps up, okay, increases up, and then decreases after the collision. So in those situations where we don't have that force being constant, we're going to be able to calculate the impulse as the area under a force time graph. And sorry, the formatting got a little funky there. But yeah, the impulse is the area under that force time graph. Okay, just one other way to calculate it. So what type of collisions maximize the force? Okay, well, in physics, when classifying collisions, there are two kind of ends of the spectrum. There's elastic collisions, which are the bouncy collisions, the ones in which something hits and it bounces off. Okay, think like a bouncy ball. Where there's also inelastic collisions, where the objects stick together after the collision. Think like a splat ball or a football tackle or something like that. But which of those do you think maximize the force? Let's go ahead and look at it in a little demonstration. And we're going to be looking at whether elastic or bouncy collisions or inelastic sticky collisions affect the bashing power or impulse that this block receives. So here's our setup. We have this little dart. It has a bouncy ball on one end with a nail in it that is removable. So I can do both bouncy collisions where it'll just bounce off the block, and then I'm hoping to be able to also get some elastic collisions where the nail actually embeds into the block and moves it. And we're going to see which of those exert more force, which of them cause the block to move farther. Okay, so before we get started, make your predictions. What do you think? Do you think the sticky collisions, when I have the nail in it, the inelastic ones, will move the block more, or the bouncy collisions, the ones without the nail in it? Go ahead and make your predictions, and then let's go ahead and run a couple tests. So we're going to start with the inelastic collisions, the sticky one. Okay, so the nail's in it. Sometimes this takes a couple tries for me to get perfect. I'll raise it up to horizontal each time. Oh, yes. That time we got it. It moved to about right there, about 5.4 centimeters. I have a ruler on the back end to check that. Let's do more than one trial so we make sure we get an accurate look at this. Okay. Okay, another good sticky one. Didn't hit it quite as well, so it didn't move quite as far, only about 2.5 centimeters. And let's go ahead and see if we can get one more good trial. Bring it up to horizontal. Oh, well, that one didn't check out. Let's try one more time. Yep, that one bounced off of it. Okay, come on. There we go. There's one more good trial. And it's stuck in. Nice inelastic collision, moved a little over 5 centimeters. So now I'm going to remove the nail and we're going to try the bouncy collisions. So do you think that the block is going to move farther or not as far? Let's go ahead and test. Zoop. Okay, so that time it only moved back right in the middle of those other two. Let's go ahead and try another trial. Okay, hit it twice, but a little bit farther than our farthest sticky one. Let's do another trial. Okay, hasn't been hitting it quite head on, so want to make sure that we get that. There we go. Okay, that time it moved quite a bit farther, about 8.5 centimeters. And then just to make sure, because that first try was a little funky, boom. Okay, that time it moved about 9 centimeters. So definitely moves farther, okay, or has more bashing power when it bounces versus when it sticks. So let's go ahead and look at the math of why that is. Okay, so as you guys saw, the block moved farther in the elastic collision than the inelastic. And let's look at why this is. So in an inelastic collision, we're going to picture this just with like a baseball or a ball of some sort. You throw it and it goes splat, okay? It then stays on the wall. So it's traveling with some initial velocity and then it goes to 0. Where in an elastic collision, the ball is traveling with some initial velocity and then bounces back off with some final velocity, okay? So if we're thinking this out, the change in velocity in the inelastic collision just equals minus that initial velocity, 0 minus that initial velocity. Where in the elastic collision, that change in the velocity will be v final minus v initial, and v final is in the opposite direction, okay? If it's a perfect elastic collision, it'll actually bounce off at the same speed that it hit at, but in the opposite direction. So we can think of that change in velocity is -2, okay? It has twice the change in velocity of the inelastic collision. So if we're looking at that impulse momentum theorem, okay, this one has a lower change in velocity, where this one has a bigger change in velocity. The mass on those is going to be the same, so the elastic collision is going to have the bigger impulse, okay? Which, if they are on the wall and have that for the same amount of time, that means the inelastic collision will be less force. Yes, that force will be over a longer period of time, which also tends to make that force less. Because if you have the same change in momentum, if you had a longer amount of time, you can use less force. That make sense? Okay, cool. Let's do one more math problem and then we will call it. So, rain is falling at a rate of 0.060 kilograms per second. If the average speed of a raindrop is 0.15 meters per second, how much force exerts on your car each second? Okay, so we have our car. There we go. Good artist here, as you can see. And there are raindrops falling on it. And we're going to go with a time of 1 second. We're looking for the force on car each second. We know the mass that will fall on that car in that second is 0.060 kilograms. Okay, that's what that says. And then we have the speed of the raindrop, 0.15 meters per second. Now, if that is the speed at which the raindrops are falling, what speed do they go when they hit your car? Well, they'll be at speed of 0. So the change in the velocity will be negative 0.15 meters per second. Okay. So in this one, since we're looking for the force, we can just use our impulse momentum theorem. Force times time equals mass times change in velocity. I know my change in velocity. I know my mass. I know my time. So I'm just looking for my force. Okay. So let's go ahead and if we divide by time here, divide by time here, that'll cancel out. So we're ready to plug in our numbers. We have that force equals the mass, 0.060 kilograms, times the velocity, change in the velocity, negative 0.15 meters per second, divided by the time, which is 1 second. So we plug that into our calculator, and we get negative 0.009 newtons. Okay, it is negative, and that makes sense because we'd had a positive velocity for the falling rain. Okay, positive velocity, and the force is, of course, in the opposite direction. So that's why it came out to negative, but that's totally fine. Okay. Okay, cool. That's how we use the impulse momentum theorem. Okay, cool. Bye, guys.